This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 2 of Week 3, Thermal Resistance Networks. We rewrite Fourier's law as a circuit, stack resistances for composite walls, and walk a worked problem with two convection boundaries. Treat heat transfer like an electrical circuit. One rewrite. Q dot equals K times A times delta T over L becomes Q dot equals delta T over R total. Temperature drop plays voltage, heat rate plays current, thermal resistance is delta T over Q dot. Why? A composite wall, drywall plus insulation plus brick, convection on each face, collapses into resistors in series. Add them up, divide delta T by the sum. Same shape as topic 1. New entries are the inside and outside film coefficients, H sub I and H sub O, plus bookkeeping rows for the per element and total resistances. Inputs up top, what you solve for at the bottom. Fill every cell and Q dot reads off the bottom row. 3 resistance forms cover everything here. Plain wall, R equals L over Ka. Cylindrical wall, R equals the log of R2 over R1 over 2 pi KL. Watch out, L here is the cylinder length, not the wall thickness. Convection film, R equals 1 over HA, 1 per boundary. Radiation can be a resistance via a linearized coefficient. The handbook doesn't tabulate it. Keep it off the ladder until topic 9. 2 bookkeeping rules. Series, heat passes through each layer in turn. Add the resistances. Parallel, heat splits across paths. Add the reciprocals to get the reciprocal of the equivalent. Same as electrical circuits. A building wall with windows and a door in parallel uses an area-weighted overall U value. Q dot equals U times gross area times the inside to outside delta T. One warning, per area R pairs with U equals 1 over R times A for Q dot. Absolute R gives Q dot as delta T over R. Pick a lane. The canonical exterior wall stack, inside to outside, 5 elements in series. Inside film, drywall, fiberglass insulation, brick, outside film. R total is the sum. Heat flow is the inside to outside fluid temperature difference over R total. Any interface temperature drops out from the handbook formula. Tx equals T inside minus Rx over R total times the overall delta T, where Rx is the cumulative resistance up to that interface. Contact resistance. Real layers don't bond perfectly. A thin air gap at the interface adds a series resistance, sometimes called interface conductance. It matters for rough machined surfaces, dissimilar materials with different thermal expansion, low contact pressure, loose bolted assemblies, cryogenic apparatus. Ignore it for smooth pre-bonded layers, like drywall on studs or mortar between bricks, cast-in or fused construction, vacuum deposited films, or when the problem gives only thickness and conductivity per layer. Caveat: it's not in Chapter 5 of the handbook, so it's out of scope for handbook-cited problems. Given a value, add it as one more series R. Worked problem. An exterior wall has 3 layers, inside to outside. Drywall, fiberglass batt, brick. Thicknesses and conductivities listed. Inside is room air at 22 Celsius. Outside is winter air at -5, each with its own film coefficient. Wall area, 10 square meters. Find the steady-state heat loss rate and the 4 interface temperatures. Build the network. 5 elements from the 3 forms, 1 over HA for each film, L over Ka for each solid layer. They sum to about 0.225 Kelvin per watt. The insulation alone is roughly 83% of our total. Everything else barely matters, which is exactly why insulation works. Compute Q dot. Then walk the temperature drops. Total drop is 27 Kelvin, so Q dot is delta T over R total, about 120 watts. Then walk the interfaces. Tx equals T inside minus Q dot times the cumulative resistance up to that point. The faces step down from about 20.5 at the drywall to -4.5 at the brick, the big drop across the insulation. Dropping the outside film lands back at -5. Final answer, about 120 watts. Sanity checks. A single 100-watt bulb covers most of the loss for this wall, versus over 1,200 watts for the bare brick in Topic 1. So 75 millimeters of fiberglass cut the loss roughly tenfold. Inside is hotter, so Q dot is positive inside to outside, every interface temperature decreasing monotonically. The biggest delta T across the biggest R. 5 traps that quietly cost points. 1. Forgetting a convection R. Problems often give fluid temperatures, not wall surfaces, so include both films. 2. Mixing series and parallel. Layers through the wall are series. Add R. Wall, windows, and doors at one face are parallel. Add reciprocals. 3. Radiation in the convection film. It's nonlinear, so keep it off the ladder, unless handed a linearized coefficient. 4. Wrong area. A plain wall uses one area throughout. A cylinder uses inner versus outer surface for the film. Log of radii for conduction. 5. Sign of delta T. Positive when delta T is hot minus cold. Flip it, and the answer goes negative. Bookmark the page. One section holds the master definition. Q dot equals delta T over R total, and the 3 resistance forms. The next covers composite walls, series and parallel, and the interface temperature formula, the most skipped piece, yet it shows up more often than the U overall form. Up next, Topic 3, cylindrical and spherical conduction. Same resistance form, but we trade the plain wall R for the cylindrical one with the log of the radius ratio. That gets you pipe heat loss with insulation, and the critical insulation radius, where more insulation can actually increase heat loss. See you there.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.